So last time I described the KKLT construction of string vacua, but since we will be spending some time on KKLT vacua and its various properties, what we will do today is to work out things in a little more detail, keep track of all the scales etc. which arise during this construction. Okay, and make sure that the approximations that we are making are somewhat controlled. Okay, and we will also see what we need to do to have this control. Okay. So KKLT construction in more detail. And we will be using mostly the 4-dimensional language. Okay, last time we discussed that the 10-dimensional and the 4-dimensional languages are equivalent. Okay, so we will be discussing today mostly 4-dimensional language. So this is n equal to 1 supergravity. And you saw that there are two functions which control the action for the scalars, okay, which are of relevance to us now. One is the scalar potential. K. The other one is the superpotential. And W was a function of the complex structure moduli. And tau, okay, tau is the action related on this is the string coupling. But not of the scalar moduli. Okay. And to make things definite, we will assume today that we have only one scalar modulus, okay, which basically means that we are working with a Calabi-Yau manifold with H11 equal to 1. Right? The number of scalar moduli is counted by H11. In fact, the number of H11 forms are invariant under the oriented form. But let's suppose that we have only one scalar form, and that's invariant under the oriented form. So H11 scalar modulus. Which I call rho. Okay. And let me also remind you of the interpretation of rho. So imaginary part of rho was essentially volume of the Calabi-Yau threefold raised to 2/3 power. This is the volume measured in ND Planck unit. Why ND Planck unit? Because the metric that he used for this Calabi-Yau volume was the canonical Einstein metric in 10 dimensions. Okay, that's what measures. So this is a volume measured in the canonical Einstein metric in 10 dimensions, which basically means that this is a volume in the measured in the ND Planck unit. So this is just to give the interpretation of what rho is. Okay. From the 4D viewpoint, of course, we will just treat rho as another field. So this goes as r to the 4, right? Where r is the radius of the Calabi-Yau. This is the radius of Calabi-Yau 3/4. Again, measured in the 10D Planck. And real rho, okay, was a scalar field which can be thought of in two different ways. The first interpretation is that we take the C4, the 4 form, and look at its component, where two of the components are on the Calabi-Yau direction and two of the components are on the space-time directions, totally antisymmetric. So this, when you decompose, it will be proportional to omega mn times some d mu of x. Okay. This will be like a massless field. So this is the 1-1 form, on Calabi-Yau form, equal. And this is a 2-form field in 4 dimensions. and its dual is real of rho, real part of rho. Okay, real part of rho was constructed, defined to be the dual of this. There is another way to interpret this, okay, which is equivalent because of the cell duality of the field strength of C4, okay, which is that it's simply integral of C4 over the 4 cycle of the 3-fold, and we don't have to say what 4 cycle it is, because since H11 is 1, there is a unique 4 cycle. Okay, there is an isomorphism between 4 cycles in 1-1 forms or 2 forms. So it's the integral of C4 over that 4 cycle. Yes, you had a question.
So omega Mn is 1-1 form or 2 form?
Well, this is a 1-1 form, but the only 1-1 form, this is a 2 form. I have not used complex rotation here. If I use complex rotation, then yes, it will be like this. Okay, but this is the only 2 form which exists in the on Calabi-Yau. Okay, there is no T0 or 0 form. Okay. So this rho will play an important role in all that we will be doing. Okay, because we will assume that the final vacuum that we get is at sufficiently large rho. Okay, large value of imaginary rho, which means that the size of the Calabi-Yau manifold, okay, at the extremum is large compared to the 10-dimensional class fluidity. Okay, because that will be our control parameter. Okay, the various approximations that we will be making will be justified based on that answer that R is large.
So 4 forms are dual to 2 forms, and H11 is 1 because we've taken only one killer
yes.
one. So
yeah, so omega Mn bar is unique. Right? So I take the 4 form, okay, and I take the 2 components in the internal direction, 2 components are in the 4-dimensional direction. So this is the decomposition. The coefficient of expansion will be a 2-form field in 4 dimension, and the 2 form can be dualized in 4 dimension to a 0 form. Right? Because dB is equal to star d of real rho. Right? That's one way of defining what real rho is. The other way to define it is that you just take the all internal components, okay, C4 in the internal direction, and integrate over the 4 cycle. Okay? That will also give a scalar field. But these 2 scalar fields can be shown to be related because DC is self-dual and in 10 dimension. Okay, that's what will relate this scalar field with that scalar field. Is that clear? So this dualization is happening in 4 dimension. Okay. If you think in now 10-dimensional duality, 10 dimension, a 5 form field strength is dual to a 5 form field strength. Okay? That's what you are using. Okay, are there any other questions? Okay, so now let me write down the Kähler potential. So this was minus 3 log minus I times rho minus rho bar minus log minus I times tau minus tau bar and minus log minus I by 2 integral of
So, but is there any way that we can see that these 2 ways of looking at it should be related? I mean,
yeah, because if you take DC, yeah,
Achha,
you will get omega, d omega is 0 of course, and omega times dB. Okay. So its dual field strength will be d of real rho. If you take this C4, right, integrated over 4 cycle, okay, so you take d of this, right, the dual of the 4 form is 2 form in the internal dimension. Okay. So that will give the omega, okay, and you will get a d phi, right, which is dual to dB. Right, so you can do the dualization in 10 dimension and you can show that these 2 are the same. Okay, so you are basically using the fact that in the internal space, this Mn component is dual to the Mnpq component. Okay? Because this is a two cycle, so it's like duality between 2 cycles and 4 cycles, right? The 2 cycle and 4 cycle intersect at a point, right, or at a finite number of points, and the direction of the 2 cycle is orthogonal to the transverse to the direction of the 4 cycle. Okay? So this direction is transverse to this. So when you dualize in 6 dimension, from here you pick up the other 4 components. Okay? That's what shows that component is relevant. Okay? And then in 4 dimension, you have to dualize, right? That they are to dualize the field strength, right? D of this, so dV to d phi, the coefficient of this 4 form over here. Okay? So we'll be using this, and then what we saw, well, then we use the form of the potential written in terms of scalar potential. So potential by V. So this was e to the k times sum over alpha I g I g bar d I w d j w bar, w is the superpotential, minus 3 mod w squared. This is the supergravity result for the potential. So let me say k I have already defined here. G I j bar is nothing but del I del j bar k. Okay, and G upper I j bar is the inverse of this matrix. Okay. Now we then divided I into two parts. One is rho, that's a single field. The other one is leveled by alpha. So alpha stands for complex structure modulus tau and various other things. Okay, this rho part we separated out. So then this potential can be written as the sum of two terms. One is e to the k sum over alpha g alpha beta bar g alpha w d beta w bar. Okay. And the important point is that this part, this has no dependence on rho. Okay, e to the k of course does have, but this one has no dependence on rho. Okay. Plus e to the k times g rho bar. Oh, I didn't define probably d phi w. Okay, so here is the d I w is del I w minus del I k times w. Okay, I defined it last time, but let me define it again. Okay. So this also shows that when I is alpha, okay, this of course has no dependence on rho, and neither does this, because del alpha of k will not pick up any rho dependent contribution, right? It will just pick up contribution from these. Okay, the second term was d rho w bar minus 3 w square. Then you use the fact that d rho w, because del rho w is 0, for I equal to rho, del rho w is 0, w doesn't depend on rho. So this is just del rho k times w, del rho k times w. Similarly, this is del rho k bar times w bar. And then we calculated these quantities, contracted with g rho bar, and showed that these two terms exactly cancel. Okay, so the potential doesn't get any contribution from this, so this is identically 0. Okay. And the only term in the potential that contributes is this one. So V is minimized at d alpha w equal to 0. because it says this, okay, which means del alpha W minus del alpha K and W is equal to 0, okay, and V at minimum is 0. Okay, and then we say that because W is in general a function of certain number of complex variables, okay, and we have equal number of equations as number of variables. For every variable labeled by alpha, we have an equation labeled by alpha. So you have equal number of variables and equations. So generically you expect that this equation should have a discrete set of solutions. Okay, solutions do not have continuous parameter in general, there is a discrete set of solutions, and all of this, those will minimize the potential, because potential is positive definite, as you can see from here. As you can see from here, because this term has gone to 0. So it will minimize the potential and the value of the potential will be 0. Okay, so vanishing cosmological constant.
That means it will give values for complex structure and tau.
And tau. And in fact, I mean, with some work one can also show that it fixes the D7 brane moduli. Okay, which we did discuss. Okay, because those are the moduli which level the position of the D7 branes along the compact direction. Because in orient T4 the D7 brane positions are still arbitrary, right? We didn't worry about it too much because there is a compact moduli, right? You can only move inside Calabi-Yau. Okay, and as I said, we will not worry about the compact moduli. But those also can get fixed. W depends on those, and those also get fixed by extremation. So generically, rho is the only modulus which is left out. Okay, in fact, all scalar moduli are left out, of which rho is one, and we are assuming that rho is the only scalar modulus. Okay, now the fact that we have a minimum and the fact that at the minimum the potential is 0 does not guarantee that we have supersymmetry. We have unbroken supersymmetry. So unbroken SUSY will require that diw equal to 0 for every I, okay, which means d alpha w equal to 0, but also d rho w equal to 0. What is d rho w? Okay, d rho w is del rho k times w. So del rho k, of course, we know explicitly it's not 0. So it requires w equal to 0. So this is of course accidental. Okay? W gives you the same number of equations and number of variables. Trying to require w is 0, okay, is in general hard. Sometimes you may find some solution for w is equal to 0, but in general w will not be 0. Okay? And we will not assume that w is 0. Okay, so we assume that w0 is the value of w at minimum. That w0 is small. Okay. Now, how can you make something small? Okay, w0 is a number, right? It's fixed. However, w0 is fixed, but it depends on the fluxes, right? Because it depends on the whole superpotential. Depends on the fluxes that you have introduced, which are integer quantized, right? H3 and F3 integrals of those along the 3 cycles should be integers, okay? And then those 3-band charge conservation has to be satisfied. Okay? But given those constraints, okay, you can change the fluxes. Okay? So while W0 is fixed, well, is discrete, okay, it is characterized by a set of discrete parameters. Okay? And you may hope that by adjusting those parameters, the fluxes, right, you may accidentally find a region where W0 is small. Okay? This we will assume because we will see that the smallness of W0 is necessary to ensure that eventually rho gets fixed at a large enough value. Okay, because that will be our expansion parameter. We will assume that the volume of the internal Calabi-Yau is fixed at a large enough value. At this stage, of course, we have not fixed it, right? At this stage, rho is completely undetermined.
This equation also not fixed.
Which equation?
D rho of W equal to 0.
So this only gives a W equal to 0, right? So it's not a condition on rho at all. Because d rho of W is this, right? Del rho of k times W. So it will require W equal to 0. So this condition in general you cannot use because it depends on the same variables, right? the complex structure and tau variables which have been fixed by the by these equations. Okay. So at this stage you cannot fix rho. Okay, unless you add something else to the superpotential which depends on rho. Okay, which is what we'll do later. Yes.
And the values that have been fixed by W minimization with respect to alpha,
Yes.
will they allow W minimum equal to 0 that is coming out from here?
Well, they may allow accidentally,
Excellent.
right? Not in general,
No, that's what you said.
right? Because you have one more equation, right? In general, there is no reason why it should be 0, okay? And we will not assume that this is 0, okay? But we will assume that by adjusting the fluxes, you have somehow made W0 small, okay? Not arbitrarily small, but sufficiently small so that it makes sense to say do an expansion in powers of W0, right? Assuming the W0 becomes small. Is this point clear? Okay. So we will see later that this will be related to the size rho. Okay. This will be related to where rho gets fixed. Okay. After we add something appropriate. So let's imagine for now that rho is large. Somehow we have made rho large. Yeah, at least at this stage, of course, rho is not fixed at all, right? So you always have a choice of working with large rho. Okay. Large radius of the parameter. And ask in that limit, what are the masses of the complex structure modular which are gotten fixed? When you say something is fixed, that means as a function, the potential has a minimum, right, at those points. Once the potential has a minimum, you can ask for a second derivative. Right? How big is the second derivative? That will tell us the masses of those fields that you have fixed. Okay, so we'll just try to estimate what the masses of those fields will be, which in fact is not very hard.
And also if W0 is not 0 but small,
Yes.
then the supersymmetry is then weakly broken.
Yes, yes, exactly. But supersymmetry is broken. So unbroken supersymmetry really requires W is 0. Okay. So at this stage supersymmetry is broken. Okay. But you will see that the supersymmetry will be unbroken once we stabilize rho. Okay. So basically after we add a superpotential, we will stabilize rho by requiring the d dot W equal to 0. Okay. So that will automatically give a supersymmetric solution. And any other questions? Okay. So if you look at this potential, okay, let's ask where is the rho dependence in this potential coming from. This part, as you have said, well, I shouldn't have written this. In fact, the correct form of the potential is this. V because we have already taken care of the d rho W term, so the V is actually sum of e to the k sum over alpha d alpha W d beta W bar g alpha beta. Okay, this was the form of the potential that we arrived at. Okay, after we showed that the rho term just cancels out, the minus 3 amount of W square term. So here, this part is rho independent. Why? Because d alpha W is del alpha W minus del alpha K times W. W doesn't depend on rho. K does, but del alpha K doesn't. Okay? Because rho dependence is just an additive term. Minus 3 log I minus a rho minus rho 1. So this part doesn't depend on rho. This one, however, does. E to the k is roughly goes as 1 over rho minus rho bar cube. And because it was minus 3 log rho minus rho bar. Okay, so it goes as 1 over 3 minus rho bar cube. So this is imaginary rho. And that you know goes as r to the 4. Okay. So this goes as 1 over r to the 12. Okay, so the the whole potential is getting multiplied by a factor of 1 over r to the 12. So the second derivative of the potential at the minimum, which determines the mass square, will also have a factor of 1 over r to the 12. Yeah, because that's after all the second derivative of the potential at the minimum. Okay. However, you have to ensure that the fields are correctly normalized. Okay. The fields that you are using are correctly normalized. Okay. So let's check the kinetic term. The kinetic term for the fields is G ij bar, G ij bar del mu phi I del mu ij bar G mu. Okay, and besides, of course, the square root of minus determinant G factor is there. So if you see the complex structure moduli of tau which appear here, okay, the fields, the alpha fields, their kinetic term contains G alpha beta bar del mu phi alpha del mu phi beta bar G mu. Okay, this is a metric in the internal space. This one has no dependence on rho. Right? It's del alpha del beta bar k. Right? It has no dependence on rho. So that's so the kinetic term is normalized in a way that it has no dependence on rho. Okay? So there is no factor of r in the kinetic term. There will be other factors because this of course can depend on the complex structure moduli and so on. But there is no factor of r, which basically means that this counting is correct. Okay? Mass square goes as 1 over r to the 12, mass goes as 1 over r to the 6. Okay, of course this mass is being counted in the 4-dimensional Planck units. Okay, because you have assumed, I mean in writing all this, you have assumed that the kinetic term or the 4-dimensional, the metric kinetic term, okay, the Einstein-Hilbert term, just has the coefficient of half. Okay, that's the way we had normalized things. Okay, so in that unit, okay, we see that the mass goes as 1 over r to the 6. Okay. So the idea now is that this mass for large r, of course, this will be small. Okay, but if r is not very large, it's not very small. Okay. So we'll assume that these fields are at this stage rho is massless, right? Rho direction is completely flat. Okay. Eventually, you have to fix rho. Okay. But we'll assume that when you fix rho eventually, okay, rho will generate a mass that's small compared to this. Okay, if rho gets a mass that is small compared to this, then we are safe, because then we can say that we can just integrate out these fields right now. Okay, all the fields which have been fixed, okay, their masses are of order 1 over r to the 6. So let's integrate them out and write down an effective field theory of rho. Okay. And if we find that the rho eventually gets a mass which is small compared to the fields that we have integrated out, then we can assure ourselves that the approximation is systematic. Okay? That we have not done something drastically wrong by integrating out these fields from the beginning. Right? Integrating out in this case will mean just eliminate by the classical equations. Set them at their minimum value. Is this clear?
But rho itself influences these masses, right?
Yes, exactly. So r is rho.
So when you are saying that rho itself gets a mass,
Yes.
I mean, how do you know that it's possible? I mean,
Yeah, we don't know it's possible, right? So we'll carry out the analysis. We'll see what the mass of rho is, and then we'll go back and check that this approximation is correct. That whatever mass rho will get, that will be small compared to this.
But it's not something you can control later.
No, not absolutely. Yeah, we have to see what it involves. Right? That will depend on what kind of superpotential generate for the rho and so on. Okay, but we will see that it is possible in principle to achieve this. Okay, that the mass of the rho will be small compared to this. Okay, any other questions? Because at this stage R is of course completely arbitrary, right? You have not fixed. Okay, so you don't even know what the masses will be. So the idea is that you have to ensure that for large R, rho mass will be parametrically small compared to this. Right? And then if we can fix R to be large by some means, then it will be guaranteed that the rho mass will be smaller than this. Right? In fact, we will see that the rho mass will be exponentially suppressed in R. Right? It will go like something like e to the minus R. Right? And hence, if R can be fixed at a large value, then that will be small compared to this power of suppressed masses. Right? So that will be the general idea. Okay, so at this stage, this is all you can get. Okay, now we will start taking into account non-perturbative corrections and see under what condition rho could have gotten a mass. Okay. And we discussed one such correction last time. Okay, but again today we will try to work out the details in a little more. Okay. We said that a possible non-perturbative correction which could give generate superpotential for rho. Okay, come from Euclidean D3-branes. Okay, Euclidean D3-branes wrapped on 4 manifolds of the Calabi-Yau threefold. Okay, there is a 4 manifold here, Calabi-Yau threefold, and it doesn't always happen, but under certain conditions, okay, one can show that if you consider Euclidean D3-brane wrapped on this Calabi-Yau on the 4th cycle, you get a generated superpotential for the field rho. Okay. It doesn't always happen because you have to ensure that the number of zero mode counting is correct. Okay. If there are too many zero modes, then that doesn't generate a superpotential. Okay. But under certain topological conditions, one can show that you do get a generated superpotential for this field.
How can we understand that this should be a non-perturbative effect?
Because Euclidean D3-branes is necessarily non-perturbative, right? That means it goes e to the minus 1 over g. Right? So you are not assuming that g is very small. Okay? G has to be somewhat small so that you have some control, right? That this expansion makes some sense. Okay? And perturbation theory, so it's non-perturbative in the sense of string perturbation theory because Euclidean D3-brane action goes as 1 over g. Okay? So the whole thing will go as e to the minus 1 over g.
But isn't it true that we want a non-perturbative correction and then hence we are thinking about D3-branes?
No. It's not that we want, in any given situation, right? We have to include all possible non-perturbative corrections, right? We are not changing the theory. You see, it's the same manifold, right? That's why it's important that it's Euclidean D3-brane. It's not that we are adding a D3-brane in the system. Euclidean D3-brane means it's like an incident solution, right? All 4 directions are Euclidean, right? It's some contribution to the path integral, right? Just like in a gauge theory, when you carry out the path integral, right? You have to sum over all possible Euclidean solutions, right? Incident solutions do have some effects, right? So similarly, here when you carry out the path integral, you have to integrate, okay, take into account the effect of all saddle points, okay? And the Euclidean D3-brane is one such saddle point, right? So don't think of the Euclidean D3-brane as anything to do with adding a D3-brane or something, right? We are not changing the background at all. Given the theory, we want to see what its effects are. Is this point clear? Okay. In the same spirit, you could have asked, what about Euclidean D5-branes wrapped on Calabi-Yau threefold, right? That's also a possible saddle point. So all of those saddle points are there, okay? But not all of them contribute to the superpotential, right? Because of the Fermion zero modes, right? In principle, you have to take into account the effect of all saddle points that you can think of. Is this point clear? Right? So Euclidean D3-brane simply means that it's a classical solution to type 2 supergravity. Okay, these the directions of the 3-brane are totally in the compact direction. Right? So it's localized in time, localized in the 4-dimensional directions. Okay, it's like in this when you do the Euclidean path integral, it's something that happens in a finite region of space time.
This is something that will only count in the 4-dimensional picture, right? I mean, if you're looking at the 10-dimensional picture, then this wouldn't have come up.
No, in 10 dimension, of course, the Euclidean distribution will be infinite, of infinite extent, right? So then it will not come up because it will have infinite action. But once you have a compact direction to wrap, right, it will come up anyway, right? It doesn't matter whether you look at it from the 4-dimensional or a 10-dimensional viewpoint. All finite action Euclidean solutions have to be included in the quantity. Okay. So if we have a Euclidean distribution wrapped on a 4 cycle, its contribution will go to the superpotential, will go as e to the power the action, e to the power minus the action. Okay, that's the typical contribution from instance, and there will be some p-factor which will not try to calculate. Okay, our interest will be in determining this. Okay, so let's try to see what this action is, right? How does it depend on rho? Okay, because you are interested in determining how it depends on rho. So D3 brain action
People have done this zero mode counting to show that there are.
Yeah, that's what Witten had done, that under certain topological constraints, right, that the zero mode counting actually allows you to have a superpotential. Okay, but not always, it doesn't happen always, but it can happen under certain scenarios.
It's plausible. Right?
Yeah, it's plausible, exactly. In fact, this condition is a condition on the Calabi-Yau fourfold. If we use this F theory picture, right, it's a topological condition on the Calabi-Yau fourfold, okay, under which this happens.
Isn't this arithmetic genus equals 1 condition?
Yeah, exactly. Arithmetic genus equal to 1 condition, but that's in the fourfold. Yeah. Okay, so D3 plane action we know is 1 over G string times the volume, right? Volume of the D3 plane volume action, unit of string tension. Okay, when you say string tension equal to 1, all D planes have tension of 1 over G string. So this is 1 over Gs times volume in string scale. So 1 over G string times Rs to the power 4. Where Rs is the volume measured in string units, the radius measured in string units. Okay, radius of the Calabi-Yau measured in string units. But we want to express in terms of rho. Rho is related to the radius to the 4, but measured in Planck units, right? So you have to relate the Planck mass to string mass, okay, in 10 dimension, and that's not very hard if you, remember the 10 dimensional relationship between the string metric and the canonical Einstein metric. It's basically GSMN is equal to e to the phi by 2 G canonical Mn. Okay, all are 10 dimensional canonical metric and 10 dimensional string metric. E to the phi by 2 is nothing but Gs to the half. So Rs is Gs to the 1/4 times R. Right? The radius is measured by square root of the metric. So this Rs to the 4 becomes Gs times R to the 4. So Gs cancels, as you can see, and this is just imaginary part of it. So this basically becomes e to the power minus imaginary part of rho. Okay, this you can then translate back to a statement about the superpotential, and what you find that this corresponds to W as e to the 2 pi I rho, some constant times e to the 2 pi I rho. Okay, which is also consistent with the fact, this normalization is also consistent with the fact that imagine the real part of rho, okay, is a periodic variable, okay, and it is normalized to have period 1. Okay, that's the typically normalized rho. So this is one possible source. Okay, then KKLT also discusses other sources. Okay, for example, gauge condensation on the D7 branes. Okay, could be another source of superpotential for rho. Okay. So the upshot of this is that we have a correction net result we have a delta W which is some constant A times e to the IC. Okay, these are constants.
And A is a constant because you are looking at tree level in the one instant on background. If one looks at loops in instant on background, that could depend on.
Yeah, but it could depend on the complex structure, etc. Right? But those we have all frozen that they are minimum anyway, right? We are assuming that all those fields we have frozen.
But it can also depend on imaginary rho. If one is looking at
On
loops,
rho, you are saying that it can depend on rho.
beyond
Yeah.
tree level, if one looks at loops in instant on background, this is tree level calculation in the instant on background.
Yeah, this is tree level calculation in instant
But
back.
in principle, if one looks at loops,
I agree, yeah. Then I think you will get further corrections.
yes,
Yeah.
that's possible.
Exactly, yeah. Loop or even one of alpha prime corrections probably could get
Yeah, that's fine.
get you one over row corrections. Yeah. Yeah. So these are leading now. Yeah.
And it's consistent because you have taken K2 log rho 2 anyway.
Yeah, exactly. Otherwise you have to correct all those.
That's-
Yeah. Okay, is this okay? So now the idea is that we take W effective as W naught, which was the minimum value that we had gotten, plus A to the I0, and K, of course, K effective minus 3 log minus I times rho minus rho bar. Okay, every other phase has been integrated up anyway, so these are good enough. And now you can try to look for a supersymmetric solution, d rho W equal to 0. Look for. And this we worked out, so I will not try to do that. So what we found that if we take the ansatz that rho is equal to I sigma, sigma being real. Okay, so you basically assume that you have a solution where rho is purely real. Then you get an equation of the form, this basically give an equation of the form this gives you W naught equal to minus A C sigma 1 plus 2 C sigma over 3. So the idea is now that we can solve for this, for sigma. Okay, we assume W naught is negative. I don't remember last time whether we took W naught to be negative or positive. Okay, if W naught is positive, we basically have to change some signs here. Okay, you have to take rho equal to I sigma plus pi or something like that, or I sigma plus 1 or I sigma plus half. Okay, so that you
It was negative.
correct. It was negative, yeah. So we have to assume W naught is negative. Okay, if W naught is positive, you look for a solution where rho is I sigma plus 1 or plus half. okay, then that will basically make this e to the 2 pi I rho and make it minus. Okay, so if W naught is negative, then we can look for a solution to this. Okay. And you can see that if W naught is small, okay, then we expect the solution to be at large sigma. And this was the reason why we wanted W naught to be small in the first place. That W naught equal to small will be consistent with the answers that it will be extremized at large sigma. Okay, and hence the fact that the assumption that we are making that R is large will be valid. Is this clear?
But this R is large compared to the Planck scale.
Yes.
This assumption, like, doesn't it go? I mean, if I want to view it as a KK compactification, then
Yes.
there should be another scale, right? Compared to which this volume should be small.
Yeah, that's the, I mean, GV scale, compared to GV or TV scale, this volume should be small. Okay. This is still compact space. Okay. But there is still a lot of space between a GV and a Planck mass. Okay. So assuming that this R is large in Planck units,
Meaning it's larger than GeV scale, but way.
yeah, 1 over R should be much larger than GV scale, right? So it's not, those Kaljuglan modes are not observable today. Okay. But nevertheless, it can be, I mean, see, large here doesn't mean that it has to be very large, right? It's just so that you have some control. Okay. So 1 over 1000 may be good enough.
And why don't you say that that is being confirmed here? That
Yeah, that if W naught is small, right? Earlier you had not justified why you wanted W naught to be small. If W naught is small, right, then the solution will be at large sigma, right? Because this is can be used to make it small. Okay? Sigma is positive, so this is positive anyway. So solution will be at small, large sigma, and sigma of course is nothing but the imaginary part of it. Right? So having a solution at large sigma means that you have achieved what you wanted to achieve.
So fluxes play no role in fixing W naught.
No, fluxes do, because W naught was the minimum of W, right? We switched on the fluxes to minimize W or not minimize W, solve for the d alpha W equal to 0, right? And we said the W naught is the value of W at the minimum, at the solution, right? And W very much depends on the fluxes, right? Because W came from this integral omega by G, right? If you remember. So that of course very much depends on the fluxes, right? Because G is F3 plus tau H3.
But the minimum is infinite.
Minimum, okay. Well, minimum is independent means, no, it's not independent because W naught depends on the fluxes, right? So the solution to this equation will be controlled by the fluxes, right? You first give the fluxes, right? It fixes W naught, and then this equation fixes sigma, right? And all I am saying is that if you taken a generic flux where W naught is of order 1, right, and this equation will fix sigma at order 1. Okay. Then you wouldn't even know whether all the approximations that you have been making are sensible or not, right? Because you are using, for example, the supergravity action, right? You have ignored all the hard derivative corrections to the action. And all of those have to be then taken into account, right? So it's necessary for the consistency of this approximation that we work in a regime where the size of the compact space is somewhat large compared to the Planck scale, right? But certainly it has to be much smaller than what is the scale that you observe today. Is this okay? So this is of course the extremization equation, but let's now try to also determine what the mass of sigma will be at the minimum. Okay, So for that it will be useful to look at the potential before extremization. Okay. So what is the potential? V of sigma, that's e to the 1 k times G rho bar del rho W minus del rho k W times del rho W minus del rho k times W bar. Right, this is the potential. This is W effective. This is not, which is the W naught plus whatever we have found. So this you can easily work out because we know what W effective is. Okay, you know what K is, and this is given by C A minus C sigma by 2 sigma square 1/3 sigma C A minus C sigma plus W naught. Okay, so they wanted to find this equation. Okay, we got this by directly solving d dot W equal to 0. Okay, but you could have also gotten it by first writing the potential completely and then extremizing this expression sigma. Okay, this extremize this has an extremum exactly at this position over here. Okay, it's as if we are using the fact that the supersymmetric condition also guarantees that we are at the extremum. Okay, so the potential extremum of the potential is, you can either get it by extremizing the potential or get it by solving the 0 of the equal to 0 condition. Okay, now to calculate the mass of sigma, that's the second derivative of the potential at the extremum, right? And the second derivative, you can see whatever you do, there will be an e to the minus c sigma factor in front. So if sigma is large, then this second derivative goes as exponential of e to the minus c sigma. Right? It is exponentially suppressed. So whatever be the value of sigma, as long as it's large enough, we are guaranteed that this mass square that we will get from here for sigma is small compared to the masses that we have fixed for the complex structure and other moduli, the tau modulus. Okay, so this shows that as long as sigma is large, which of course requires some effort, right? You have to make sigma large by choosing W naught to be small, by adjusting those discrete fluxes. But as long as you have done that, then we can expect that the mass of sigma is small compared to the masses of the fields that you have eliminated by equation of motion earlier. Okay, so this shows that this approximation at least is internally consistent. Is this point clear? Okay, so we also wrote down last time the result for the P at minimum. P at minimum. Okay, which basically means that you evaluate this at the solution to this. This was minus 1/4 c square a square to the minus 2 c sigma, sigma equal to sigma minimum. So this is the minimum value. This is okay, and this negative side here guarantees that this is ADS 4 right? Okay, because potential has become negative.
Like we saw the masses of the other molecules that were fixed.
Yes.
It goes like 1 over R to the 6.
Yes.
And hence like a.
So those are powered or suppressed for large R, whereas these are exponentially suppressed for large R. Right? So that's the difference. That's the reason why you can parametrically keep these smaller than the others. Right? But again, parametrically is a little strange word because the only parameter that you have to vary is this W naught, right? And that in turn is a discrete set of variables, right? This is fixed by the fluxes. Okay, so you just have to hope that somehow the fluxes, by adjusting fluxes in some given model, you may get a small W naught, and only then you can do all this.
But why is it required that the masses should be small of this model?
Because if the radius is not large, as I said, all the higher derivative corrections are going to be important, right? So radii better be fixed at large value, right? And then having the masses of the complete structure moduli larger than this, that's just a convenience that we assume that we can first eliminate all those moduli, right, and then work with an effective theory of rho. But if this effective theory has the same order of masses as the ones that we have eliminated, then we should really do it together. Right? So this hierarchy. Okay, so this is ADS, but that's not what you want, right? You want a de Sitter solution. Okay, so you have to now learn how to lift it to de Sitter. Okay. And this again we discussed briefly last time, and that we do by adding anti-difference. So adding anti-difference, okay, you should really think in terms of, see, you cannot just add an anti-difference, but once a flux has been fixed, right? If you just add an anti-difference, you will not satisfy the difference charge conservation, right? You saw that there is a condition that fixes the total flux plus total difference charge, right? And this has to do with the fact that if you have a space-filling brane, okay, then it generates a tadpole, right? Just like you cannot put a point charge on a sphere, you cannot put a space-filling brane. It has to have at least the flux that it produces has to go somewhere, right? And if there are no non-compact transverse directions, then the flux has nowhere to go. Okay? So you should really think in terms of adding a D3 broad pair. That you can always do. D3 plus anti-D3 will do the job, but we don't want to do that because D3 broad pair has tachyon on it, okay, and it will be annihilated almost immediately, right? So you think of as if you are adding a D3 broad pair. Okay. But the D3 brane that you are adding, okay, is not staying there as a brane, okay, it's staying as fluxes. Okay. So which means that you modify the fluxes in such a way that you increase the D3 brane charge that is carried by the fluxes by 1 unit, okay, 1 unit more than what would have been needed for the conservation law, and you compensate for that by adding an anti-D3 brane. Is this point clear? So, as far as charge is concerned, it's as if you are adding a D3 broad pair, but as far as dynamics is concerned, you are adding a D3 broad and changing the fluxes so that you compensate for that in the fluxes.
And this thing is being on top of this, I have already obtained a ADS4 vacuum.
Yes, so imagine that you have already obtained ADS4 vacuum and then you are doing this. Okay, but there you have to do this, carry out this process. Okay. So now the question will be, what is the effect of adding this anti-D3 brane? What it will do is that it will give an extra contribution of potential because it has tension. Right? This anti-D3 brane this time is space filling, right? It's not the Euclidean D3 brane that we considered earlier because that was an Euclidean solution that is wrapping the internal space. Now we are really talking about genuine anti-D3 brane that is filling the space-time volume. Okay, so this is situated at some given point on the internal space. Okay. So it will raise the energy because anti-D3 brane carries tension. Is this clear? Right, so it will raise the energy by something like 1 over G string times integral V4x equal to determinant of G10, but let me call it determinant 4 of G10. The string metric, okay, is the metric in which the tension is 1 over G string. Okay, but you don't want to consider the determinant of the full 10-dimensional metric. You are only interested in calculating the determinant of the 4-dimensional part of this determinant, because anti-determinant extends only in the 4 directions. Right? These are the 4 directions around the space-time. So that's what we mean by this. Okay, that you have to use the string metric, not the canonical metric, but you have to calculate the 4-dimensional determinant. Is this okay? But this formula is not quite correct, okay, and that has to do with the fact that we should really think of this as adding a D3 bar pair on top of the supersymmetric vacuum that we had. Okay. We are effectively adding not just an anti-D3 blend, because that will not conserve charge. We are really adding a D3 bar D3 pair. Okay.
Which will need W naught to change, because the W naught is fixed in terms of those fluxes, which will also change.
Yes. So if you want to do that, it's a very complicated process. Okay. But there is a simple argument which says that effectively what it amounts to is adding a total energy which is twice the tension of the anti-D3 blend. Okay. Because it's like we had some original vacuum, and on top of which you are adding a D3 bar pair. Okay. So total tension that you are adding, okay, over that supersymmetric vacuum that you had to begin with is twice the tension of an anti-D3 blend. Okay. If you are not worried about factors of 2, etc., okay, you can forget about this factor of 2, but this is, if you want to do everything systematically in a given, any given compactification, you have to keep track of this factor of 2.
So aren't the tensions of D3 and anti-D3 opposite?
No, tensions are the same. The charges are opposite, right? But tensions are of course energy per unit volume, right? That is the same for D3 and D3 bar. Okay, that's why D3 D3 bar, adding D3 D3 bar doesn't generate any Raman tadpole, which is equivalent to saying that this extra D3 blend charge, if you spread around in the fluxes, you still cancel Raman charges. Okay, but you have an extra energy. Okay, so what this factor of 2 represents is that as far as the extra energy that you produce is concerned, okay, it doesn't matter whether the D3 blend remains as D3 or whether it gets spread out in the fluxes. Okay, supersymmetry essentially guarantees that it gives the same amount of excess energy. Okay, but in any case, we will not worry about these factors of 2, etc. Okay, so we will do a crude estimate, because our essential goal will be to determine the dependence on sigma, right? Because that is the parameter which is unfixed, right? We will not even try to keep track of factors of G string, because G string has been fixed at some level, right? And we are assuming that it's somewhat less than 1, so that perturbation expansion makes sense. But we have not specifically said how small it should be and so on, right? So G string will ignore. We will be mainly interested in keeping track of the factors of rho that comes in converting this metric to the 4D metric.
And in this effective action, the vacuum term is dropped because by hand.
No, because the point is you don't really have a D3 blend, right? The D3 blend is spread out over the whole in the flux, right? And anti-D3 blend in the flux background doesn't have any obvious tachyon. You know, that was all of this argument about Bena et al. Right? Whether the anti-blend in flux background has some instability. Right? And then the recent paper of Bolchinski argued that no, there is no such instability. So that's why if you really had a D3 blend, then of course there will be tachyon. Right? So the idea is that there is no D3 blend. D3 blend is spread out in fluxes. But as far as the energetics go, okay, even after spreading out the D3 blend in fluxes, it still contributes an excess energy, which is equal to the tension of the anti-D3 blend. Right? So you add to the original energy density twice this amount. Okay, as I said, this is only if you want to do everything, keeping track of all the factors that you need to take into account this factor of 2.
And one can show this factor is actually 2 then.
Yeah, this was I think done by, probably it is already there in this Castro Pearson Verlinde paper. Yeah, that when you add an anti-D3 blend, it's effectively
To leading order.
Yeah, to leading order, this gives a factor of 2. Okay, so let's forget about G string as I said. Okay, let's try to quickly work out what will be the row dependence of this. Okay, so G string, let's set it equal to 1. Okay, let's not worry about G string. So if you set G string equal to 1, then this is the same as G canonical at 10, right? G10 canonical up to factors of G string. Okay. So what we need to do is to find out the relationship between this, the 10-dimensional canonical metric, and the 4-dimensional canonical metric. Okay? Because we want to express in terms of 4-dimensional canonical metric. Okay? Because the 4-dimensional canonical metric is the one which has been normalized correctly. Right? Because we have to set the 4-dimensional Planck mass equal to 1. So if you just directly dimensional reduce, okay, the 10-dimensional action. So suppose you start with the 10-dimensional action, square root of determinant G10 canonical and R10 canonical. Okay. What we will get is roughly a factor of R to the 6, that is the volume of the Calabi-Yau, times integral d4x square root of G. This is the determinant 4 of G10 canonical R4 in G10 canonical. And these are direct dimensional reduction. This R to the 6 came because we have a volume integral over the 6-dimensional internal space that produces the R to the 6. Okay. And now the idea that we find the relationship between the 10-dimensional canonical metric, which appears here, and the 4-dimensional canonical metric by scaling to get rid of the R to the 6. Okay. And that you can easily check that if we define G10 canonical as R to the minus 6 times G4 canonical. That will basically get rid of the R to the 6. Okay, why? Because square root of determinant G10 will become a R to the minus 12 from here. Okay, but there is a, in this R, right, there is a G inverse. Okay, will pick up an R to the 6. So that R to the 6 and R to the 6 will cancel the 1 over R to the 12 that comes from here. Okay, this is a standard thing that you can easily check. Okay, this is also the reason why when you try to remove the delay term, for example, from the 4-dimensional metric to put into the canonical metric, right? You define G string as e to the 2 phi times the G canonical, right? Whatever was a multiplicative factor in the action, that is what appears in the scaling. In 10 dimensions, the scaling would have been different because this would have scaled different. Right? But in 4 dimensions, this is what you have to do. Is this clear? Okay. So in this, we can now see that square root determinant G10 will go as 1 over R to the 12. Right? Because this goes as 1 over R to the 6. Determinant will be the 4th part, 4-dimensional determinant, then we will take a square root. That's 2 part, 1 over R to the 12. That is 1 over sigma cube.
R4 G10 canonical becomes with this value in the background. So it's a because you're matching with this action in the first line, right?
Yeah.
So what happens to the R?
What happened to the R?
No, sorry, you're matching with the expression in the line 1 on the top of the blackboard, right? No.
No.
Oh.
Yeah. This is the equivalent tensor. So that That comes only at the end, right?
Okay.
Now I'm looking at the 10-dimensional supergravity action.
Oh, so canonical normalization and kinetic term.
I canonical normalizing kinetic term, the Einstein-Hilbert term. Right? So this reduced to R to the 6, and then I said that if you scale it this way, then you get the canonical normalized kinetic term. That fixes the relative scaling, and then I am using it to evaluate this distributed tensor. So this basically goes to 1 over R sigma q. Is this clear? Okay, but there is one more effect which you have to take into account. So you say this is the 4-dimensional metric, right? You have defined this 4-dimensional canonical metric by this overall scaling. Okay. But this is only the 4-dimensional canonical metric on the average. Okay. Remember that the kind of compactification that you have been considering is what? Okay. So this 4-dimensional canonical metric is not eta mu nu, right? But it is eta mu nu multiplied by some warping factor, right? Which depends on the internal space. Okay. So this factor is 1 over sigma q, but it will get a contribution of the form a naught of y to the 4, where a naught of y gives, let's say, a of y. This is a warping factor, because the metric is not eta mu nu, right? If the metric had been eta mu nu, then this would have been just, once you have converted to the 4-dimensional canonical metric, you declare it as 1. Okay. But the metric is not eta mu nu, right? Metric is eta mu nu times a warp factor. Because of the warp factor, we have y dependence. Okay, so different tension, so that the potential that it generates is this. So this basically says that the anti-decrepitance that we have added is not going to stay anywhere in this compact space. It is going to come and sit at the minimum value of this. Right? Because you have generated a potential for the anti-decrepitance, but the position of the anti-decrepitance on the compact space is a scalar. Is a scalar field. Okay? That scalar field sits now, that generates a potential, that has a potential given by this, and it sits at the minimum of A of y. Is this point clear? Okay, this came, if you just look back and look at the form of the metric answers that we had taken initially, right? The GKP metric answers. It had the eta mu nu was multiplied by a factor of e to the 2a, right, which depended on the y. Okay, and that we had a differential equation that gives the solution for a. And now the point is that we have one more thing to play around with. But it turns out that by adjusting fluxes, we can actually generate large warping. Okay, which means that we can, by adjusting the ratios of fluxes appropriately, we can ensure that the A at the minimum, okay, is a small number. Okay, and that's what we will exploit. So the potential that the D3 broad brain generates, okay, goes as 1 over sigma q, okay, which is of course already small because there is 1 over sigma in the there is sigma in the denominator, but the coefficient can be made small, okay, by appropriate warping of the metric. No, I shouldn't have erased the potential, I have to write it again, doesn't matter. Okay, so delta V goes as some P over sigma q. D can be made small by 1. And again, this is controlled by fluxes. So V then now is V naught plus delta V. And V naught was the original potential. So let me write it again. C A to the minus C sigma 2 sigma square. And this delta V is plus V over sigma cube. Oh, sigma cube, sigma to the 4, sorry. No, this is correct. Yeah.
Can you explain? I didn't understand. This small warping, this D can be made small by warping.
Yes.
How is it controlled? By
Because the warping, right, is how the scale factor, that e to the 2a that we introduced, varies in the internal space, right? And that, if you look at the differential equation that determines that A, that depends on the fluxes. Because the fluxes enter through that, and there is a well understood mechanism, right, which generates this large warping, which is called this Klebanov-Strassler throat. Right? So there is an appropriate flux you can choose. Okay, it essentially depends on the ratios of fluxes through some cycles, that you can make this A become very small in some region. Okay, and that's what you use to control your T. Is this clear? Okay. Again, it's a discrete parameter, right? Because the fluxes can be only changed by discrete amount. Okay, and you don't want to make D too small, okay, because D has some purpose, right? So what is the purpose of D? Okay, so this gives a positive contribution to the potential. Okay, so the idea is now that we have to re-extremize this combined thing and ensure that at the minimum the value of the potential is positive. And that's what gives the de Sitter extremum. Okay, it's not guaranteed, of course. If you choose D in the wrong way, it will still remain negative, right? If you choose D to be too large, it may become too positive, right? Sometimes you may find that the extrema has disappeared, right? None of those you want. Okay? But by adjusting D appropriately, you can try to ensure that you have an extremum, and the extremum is little bit above 0, okay? Precisely the one that you want, that you need for today's cosmological constant. So that's the basic idea of this kind of construction. But of course, this is more general, right? It need not be. It may be that this is not what actually determines today's cosmological constant. Right? There will be some other mechanism. But this is a general procedure of how to construct de Sitter vacua in string theory. Right? You may also try to use it for inflation, for example. Right? Well, inflation is not a good idea because inflation requires a flat direction. Right? This is of course not doesn't have a flat direction, but you can use it for this eternal inflation. Right? What people use for multiples and so on. Anyway, so what you use it for is not the question, but this tells you a way, gives you a way that you might get de Sitter vacua in string theory. Is this clear? Okay, so let me just do one more thing and then I'll try to stop, or maybe two more things. Okay. So let's see how much sigma will be shifted. Okay, so let's see how much is, so that we can say anything about delta sigma. Now, the minimum of this is del V naught del sigma plus del delta V del sigma equal to 0 at sigma equal to sigma naught plus delta sigma. Right? Okay, so let's suppose that delta sigma is small, okay, and try to determine delta sigma, then we will go back and verify that delta sigma is indeed small. Okay, so let's try to calculate this. So this is, we are assuming that this is, this gives you some additional contribution. So del V naught del sigma is del 2 V naught. See, del V naught del sigma is 0 at sigma naught, right? By definition, because sigma naught is the minimum of V naught. Okay. So this is del 2 V naught del sigma square at sigma naught times delta sigma plus del del V of del sigma of delta V, that's minus 3V over sigma cube. So delta sigma is roughly, sorry, 3D over sigma to the 4. 3D over sigma to the 4 over del 2 V naught. Okay, so let's now try to see if this is small or not. Now you see that if you want to take the second derivative of this, okay, there are various sources of second derivative. Okay. But what you would like to have, you are trying to get the maximum possible contribution, right? The maximum possible contribution will be the dominant one. Okay. So the maximum possible contribution will come when the second derivative term acts on the exponent. Because acting on the exponents, it only brings you back factors of c, right? Instead of order 1. Right? If it acts on any factor of sigma, it kills a factor of sigma, right? So it will reduce the value, right? So the maximum value of maximum del 2 del sigma square you can get if you act the derivatives on the exponent. Okay? So roughly you can say that this quantity goes at c square times v naught, roughly. Okay, the derivatives are going to bring you factors of c. This one, okay. Now let's forget about this one. Now we have assumed that the sum of the two gives a cosmological constant which is small. Right? Imagine that we are trying to reproduce what we see, right? Sum of the two is very, very small. Okay. So which basically means that d over sigma naught, sigma cube is close to minus v naught. Right? If we want to say sum of the two to be very, very small, right? Then you need a very fine cancellation between these two. Okay? We'll try to get some number like 10 to the minus 120, right? That's the present cosmological constant in Planck units. So then this will be roughly v naught over sigma, because d over sigma cube is roughly v naught, times 1 over c square v naught. That's like 1 over c square sigma. Right, that's a rough estimate of this. C is of order 1. So if sigma is large, which is what we had assumed, then you see the delta sigma is small. Right? It goes as 1 over sigma. So that basically means that the re-extremization of v naught plus delta v does not change the minimum that much. Okay, so whatever we had done earlier, okay, is more or less valid, and all that happens is that this is basically going to add an extra contribution of d over sigma naught q to the potential, and that you have to adjust that to cancel off the negative cosmological constant to as fine an accuracy that you need.
This statement that V naught plus delta V must be very small. That,
That comes from the fact that demand that the present day cosmological constant is very small.
but is it obvious that, I mean, this will be satisfied because that almost says that you're,
Yeah, it's not obvious at all. You need high degree of fine tuning.
Right? This C's and A's must be, W, G's must be very
Finely tuned, exactly. Yeah.
Otherwise it's almost like, I mean, sigma is,
Yeah,
is the
so
order of
I mean,
sigma.
so far what we have done didn't need any fine tuning, right? We just said the W naught has to be small, maybe not too small. We just want to make sigma somewhat large, right? Now, if we want to make this into a real cosmological constant problem, right, we really need high degree of fine tuning, right? So what it is saying is that at D, the fluxes have to be adjusted precisely in such a way that the sum of the two is very, very small, like 10 to the minus 120.
Yeah, because almost like if you take the common sigma factor, is almost like sigma is proportional to e to the sigma. I mean, if the only
Well, no, the D can be made small, so you see.
you have to fine tune those. then
Yeah,
A
because
and-
D, we have the watt factor in front with us, right? So D can be made small. So sigma is not necessarily e to the minus sigma. Right? That even though it looks like this is much smaller, for large sigma this looks much smaller than this. But as long as D is small, then you can still have a consistent way of cancelling the two. Okay. Nevertheless, we need a very high degree of fine tuning, right? That no one is denied. I mean, you cannot just get cosmological constant of e to the minus 10 to the minus 120 with no work. Okay, so this is just showing that there is a possibility in principle in string theory to get de Sitter vacua, right? Not giving a model for de Sitter vacua, or not giving a model for the vacua that we are living in. Is this clear? Okay, so finally, okay, let me just say that this potential, okay, that we have gotten, so you can plot what how it will look. And it basically has a shape like this. D versus sigma. We are assuming that the minimum is positive and small. Okay. So as sigma goes to infinity, of course it goes to 0. That is the decompactification limit. Right? Sigma goes to infinity corresponds to when a Calabi-Yau has become infinitely large. That's the 10-dimensional decompactification limit. We are somewhere here. This is our sigma naught plus delta sigma. Okay. And from this picture, it's clear that there is a tunneling probability. Okay. Even from this picture, you can just tunnel out. Okay. So that's a possible instability of the de Sitter space. Okay, that it can tunnel into a vacuum which is a true vacuum, or at least which is lower than us. But this is not the only possible instability, right? There are other possible instabilities possible. For example, the anti-brane that we added, anti-D3 brane, right? That could combine with the flux and disappear. Right? As far as charge conservation is concerned, if the fluxes adjust themselves a little bit, and so that the anti-D3 brane charge is cancelled, right? It can disappear into a flux vacuum, but the anti-D3 brane has disappeared. So that's another possible instability of this kind of construct.
Yeah, why won't that happen immediately? I mean,
Because they are not tachyonic mode, right? You have to actually work out what is the effective potential, what are the, basically you have to look for the Euclidean instanton solution which takes you from this configuration to the other configuration. Okay? See, all you can say is that as far as charge conservation is concerned, that possibility exists. Right? That anti-D3 brane can annihilate with the flux and become just pure flux, right? Some ADS vacuum somewhere else. But you have to calculate the probability of this decay. Right? And you have to make sure that all of these decays that are possible are not possible here. Okay, or they may be possible, but their lifetime has to be larger than the lifetime of the universe, right? Because we have at least lived for 10 to the 10 years, so it better be that the half-life of this is at least 10 to the 10 years. So to study these questions, you have to learn how to calculate this decay amplitude, right? And that's what I'll try to do during the next few lectures. Okay, that is a general setup. Okay, but this question, of course, is specifically true here, but it's also a general question in a quantum field theory. Okay? You can always imagine that you have a quantum field theory where the potential as a function of the scalar has two minimum. Right? And you can also imagine that this is a minimum that describes us, okay, which is perfectly consistent as long as the decay probability is sufficiently small. Okay, but nevertheless, if you want to know what is the decay probability, okay, you have to learn how to calculate the transition probability from here to here. Okay, so that we'll try to study next time, and the same idea can then be used to study various problems of this.
But that then there the constructions has to be modified because here in this picture,
Yes.
like if we tunnel from sigma this present thing, we go to some runaway thing.
Yeah, but to calculate the decay probability, essentially what is needed, right? It's like a WKB, right? You basically tunnel here, okay, and then you go do classical runaway, right? So the quantum tunneling probability, right, is essentially to study this part of the problem.
And is this saying that is a multivariate like lots of backward corresponding to different choices of D in some sense?
No, multiverse idea is that if you have a vacuum with a large enough cosmological constant, right? By that, well, this is a generic construction of DC, right? You can have a vacuum with large enough cosmological constant, which can go into the same vacuum, but that can tunnel into many different other vacuum, right, of lower energy. It doesn't have to be that the only transition happens into one particular vacuum, right? So if you have a large cosmological constant that is expanding rapidly, right, and during that expansion, it can make transition into various other vacua. And what we can show, if the decay probabilities are not too large, right, then the expansion of the universe can compensate for the fact that there is continuous decay going on in various parts. So we'll see exactly how the decay takes place. That it's not that the whole universe at one go becomes goes to the other phase. Right? It happens through wobble nucleation. Okay? So that we'll study tomorrow. And so the multiverse idea is that as long as the initial vacuum doesn't completely disappear, right, more and more new vacua could be produced as it expands.
So, have people explicitly calculated cosmological constant ds space for d?
No, not. I mean, if you want to know if somebody has calculated the cosmological constant and that reproduce 10 to the minus 120, no. Absolutely nobody has
But
done.
any positive value?
Yeah, this KKLT construction, right, I think they looked at some specific example and they got a positive value, but they have to choose fluxes etc. to get D appropriately. Yeah, and then again there are questions of whether you have taken into account this correction, that correction, right? So you have to be very careful to make sure that you have all the corrections in place, right, and gotten the answer result.